I bet you dollars to donuts would be nice to have once we get Michael.
Dollars to donuts?
Yeah, I don't know what that means either. But
it's a
what's it from?
Is that like Apple Store?
Well, it's like a ration thing. Like your odds are 10 to 1. Well, I'll bet you dollars to donuts. I'll give you dollars if you give me donuts. That's how short I am.
Confidence.
Well, excellent. Now I feel all better. Now that I know that I was using.
Is that? I bet dollars for donuts.
Yeah, it's a figure of speech, but it's basically like your odds in a gambling run. It's 10 to 1. It's like you give me $1, I'll give you donut, or I'll give you $1 paid with donuts. You still have a better odds.
When donuts were only 10 cents, maybe.
But I'm confident I'll win.
There's also an expression which somehow Australians use, and Steve Crothers in particular, in one of the emails he wrote, I bet London to a brick. So it's like,
wow, that's a good one. Yeah, it's very similar to that. Similar idea. Well, I bet London to a brick then that we'll get more activity after Michael Goodspeed's on our show. He'll probably want us to go onto his show just to talk about what we do. Welcome to the October 21st edition of the Electric View. I'm Neil Thompson. Today we have Robert, Jim, Heather, Edwin, Robert Sr., Eugene, and David. We will be talking about cosmic rays and other electrical effects on life, the properties of plasma itself, and Peter Mungo Jupp's EU 2017 presentation on electric fossilization. Please like and subscribe. Like Dave's videos even, whatever. If, feel free to just spread it around a bit, because that seems to be the way that things go when we start sharing the videos to other, linking them to other videos and so forth. And not that I'm saying you have to do anything.
No, but I think I made some friends doing that, because people from other groups are interested in the same type of topics and might not even be aware of the electric universe theory.
Exactly, yes.
But they're sharing things that are along the lines, and you're like, there's like a whole group of people. So you just kind of start chatting with them and share some knowledge. And I mean, I have had people just I have like a bunch of friends in India all of a sudden, because you just start
me too,
meeting
actually.
people. It's pretty cool. Yeah, I made friends. That guy in New Zealand. I've been making friends all around the world from just sharing stuff. Not invasive, not rude, or just hey, we totally were just talking about this the other day. Check out our video.
Right.
Yeah, cool. Stuff like that. And we don't want to be, we're not trying to make, make bank or anything. So it's just no advertisement campaign. It's just you guys are like, we're just sharing for the love of.
You always virtue signal, Neil.
Thank you.
Yeah, I feel like the jackal here. I am trying to make bank, actually.
Yeah, well,
it's a survival thing.
No, I understand, and I recognize that. I basically, in a way, for me, it's a way of basically saying, "Hey, ego, don't even think about that. You don't even think about that, because it's not going to happen. And if it does, surprise, yay."
It's like materialization or something.
I just don't want to pollute it with my own.
I think that's a common thing, like consideration of what that is. Like as far as if you go out and in order to monetize something, right, that you believe in, mm-hmm. This is it's an interesting dynamic, and it's certainly got charge around it. But if you want to devote your life to something, how do you survive doing it?
That's a good point.
That's the question, right? And usually it's the more esoteric it is, the more difficult it is.
That is indeed quite a question there.
Yeah. So
now, speaking about survival and Dave and stuff, I mean, maybe it's not a very comfortable topic to talk about, but maybe it's actually, his condition is related to this, minimum of solar activity that we're diving into. I mean, the cosmic ray influences strokes and so on. So
I never even thought about
anybody
that.
of you have any?
It's a really that's a really interesting that one I'm particularly curious about, just as far as the solar minimum and health, particularly cardiac. You know,
it also
okay. Sorry.
No, here. Okay.
The Thunderbolts project has come out with Peter Mungo Jupp's speech in the 2017 conference, and I know
was just watching it.
Spoke about the people going insane and just dying and everything, short circuiting out. But that could be, from the same electrical, effect that could cause that.
Well, it's if you could think about imagining the if for example there was a ripple going across the atmosphere of pressure. And even though this is not true in any shape, form, or imagination, but you could imagine physical pressure vibrating up and down, like between 14 and 20 psi, and just bouncing up and down every, let's say, few hertz, several times a second. It would just mess us up. I mean, we couldn't take it. Our bodies are not made to deal with that kind of stuff. Now,
right.
Putting that into an electrical pressure system, if electricity has a lot to do with the way that our bodies work, and that in this relatively moderate stage, human beings are this resilient, and our lives are this long, or our health is dictated this much. Certainly, in times of catastrophe, perhaps maybe things like that were happening from that point to almost to the point where how you electrify chickens or taser people or cow prods, from anywhere in that scale, God knows how we would react to it. I certainly don't think it would be good.
Probably not.
But I do notice people who are having medical issues or have previous nervous system issues, cardiac issues, things like that. I do notice from watching the weather, the space weather, and my friends and my family, that things that they are affected, whether they know it or are cognitive of it or not. I was actually just talking about it this morning because we are at KP0 right now, and we have been for a couple days, and one of my family members is quite ill and is being affected today, and my other family member who has a nervous system issue is having another, they're both just extremely pushed right now. And it's okay, so it's telling my mom, I'm I look at the space weather and things like this, so that on days like these, I know just to be a little bit more patient with them, to be a little calmer with them, and a little bit more compassion with them, because they're having a really hard time, and they probably don't even realize this, that this too shall pass at this moment. They don't know about this
cycles,
charge happening, right?
I wonder if we can get statistics on stuff like this, as opposed to averages. Do we have more on certain days? Can we? Because I don't know if we even put these things together, but it shouldn't be hard to figure out worldwide strokes and to see if it actually follows a pattern, a pulse, a heartbeat, if you know what I mean, a sawtooth waveform or something like that, or is it more of a sine curve, or is it even that at all? Are we just delusional in thinking that's the case? Is it all in our heads? If you know what I mean.
Well, go back to last year's massive CME in September, and then go through major cities' health records and see if there was a jump in any health conditions.
It's stuff like that. I wouldn't even know where to start, but that would
hasn't SO been looking at this? I mean, I remember from someplace where Ben Davidson was talking about it.
Yeah, and the heart conditions.
One of the recent past, yeah.
At the last conference, there was Dr. Edwin D'Amico speaking, and he gave a presentation on the medical effects of space weather, and it was pretty well founded in the sense that he was discussing, the correlation versus causality thing, and so on. So people have actually found a lot of correlations, and in particular strokes with cosmic ray flux, but so far it's just not clear how it is, physically, how it is realized physically or biologically, if you like. But there's definitely a lot of papers, and if you just Google again, like cosmic ray stroke or something like that.
Oh, put in just put EU 2017 after that if you want to try to find them at if there's a posting about them.
That wasn't not EU, it was OTF, Ben Davidson's Observing the Frontier.
Oh, well then it's right there. I didn't know. I'm sorry, I thought it was the EU conference. My bad.
So you would find a lot of papers like that, basically. That's what I'm saying.
Well,
But
obviously
again,
people studied it. Look at that.
yeah, again, how they are related, it's not clear at this point. So yeah, and Heather mentioned KP index, for example, but well, KP is only like a very, very secondary proxy for cosmic ray flux. Because, well, KP obviously shows you the geomagnetic activity, right?
Right.
So it's not directly related to the cosmic ray flux, although it is related in some way, in the sense that geomagnetic activity is regulated by solar activity, and so are cosmic rays, you know. So when there is a high activity of the sun in terms of, you know, stronger solar wind, more the stronger magnetic field of the sun, then there is less cosmic rays because of Forbush decrease.
Right.
Because the solar plasma kind of sweeps out the cosmic rays, the particles from other stars, essentially.
Right.
So in this sense, KP might be a proxy for cosmic rays, but there are lots of, you know, actual instruments that measure the cosmic ray flux itself. So in this sense, it's kind of not reasonable to look at KP. That's what I'm saying.
Right.
Trevor was making that argument the other day, too, on one of the sites.
Well, I was just thinking that it was associated because if the wind wasn't blowing it away from us, then we were just kind of sitting in it. Like if the cosmic rays, whatever degree that they were coming in at that point, without the solar wind to blow them away, then it just became like a stagnant atmosphere of us in it, or no protection, I guess. Like it's not blowing,
just sucking it all up. Yeah,
exactly.
And it's pretty much like that. I mean, right now, I mean, Ben Davidson has multiple times correctly indicated that there is a maximum of cosmic ray flux right now in all of the history of their observation, like since the, I don't know, maybe 1940s when they were first detecting those cosmic rays because of the super low solar activity.
Right, which of course then has a lower magnetic shield of the Earth, which makes sense because the lower the field strength, the less reactance that you're going to get as the high energy particles go through the atmosphere. So that makes sense. Basically, it's like having less resistance to it. In a sense, although reactance is not necessarily resistance, but you know what I mean.
But the Earth's magnetic field actually gives much lower protection from cosmic rays than the solar magnetic field.
Clearly, yes, it's much stronger.
Like an order of magnitude smaller. Yeah.
Well, yes, I just remember when Todd asked that thing on the page there, and you said, "Well, I think of cosmic rays," and then I went and decided to look up cosmic rays to make sure that I was like, I think they're high energy, because I remember high energy ions from Don Scott's work when he was postulating where they arrived from, like where do cosmic rays come from type thing, you know, like and that type of thing. But you're right, it's clearly the heliopause is the big barrier, and obviously the flux of the magnetic field of the sun would probably redirect it much more than the Earth, given the magnitude of their scales. Yeah.
Well, my answer to that, and for everyone just kind of to be on the same page, Todd Kleckner asked on his Facebook page, what do you imagine first, I guess, when you hear cosmic rays? And I've answered, well, cosmic rays.
Yeah.
I had to throw in a little humor there. I said really hot sauce.
Yeah. Well, basically, my answer was motivated by the fact that I've been researching this topic a lot. So, you know, I already have so much attached to it that, you know, I kind of recognize these couple of words, cosmic rays, as a whole separate kind of thing. So
Yeah, that happens. I like the fact that he's asking it. There's something about getting the concepts right that we talked about before. About does the nomenclature actually match the what we're actually seeing? Is a solar wind really a wind type stuff? If you get my meaning. Those type of questions. Words matter, I guess, is what I'm saying.
Words are boxes.
Yes, conceptual boxes.
Words matter, though, unbelievably, because when you give something a name, you identify its unique qualities, and you separate it from all the other things that might have a similar qualities but aren't quite exactly that. So words are very important, and words are very powerful, and that's why I always talk about like Birkeland currents. Like, should we call them all Birkeland currents, or could Birkeland currents be like a hood? Shouldn't there be like subsections of these things to better describe the particular function of that type of current? If they're all Birkeland currents, then that's like
you hit the nail on the head. That is exactly what I was thinking about. I had a gentleman who was on my page, just and he said, well, the Birkeland current that's going up and around. I go, no, that's not a Birkeland current. That's just a coil of copper wire. That's not a... I understand what you're saying. I recognize what he was trying to say, but it's not a force-free aligned current, if you get my meaning. It's just a coil, coil.
Yeah. Actually, what I've noticed is that in the EU community, people speak of Birkeland currents. When they speak about Birkeland currents, they mean basically what is recognized in physics as field-aligned currents. And by field, it means magnetic field. So the Birkeland current in the EU community means a current aligned to the magnetic field in like mainstream physics, basically. So sometimes I actually would say that field-aligned currents is kind of a more simple, maybe more recognizable thing, because in mainstream physics, when you hear Birkeland currents, these are the particular currents in Earth's magnetosphere, that fall from the auroral ovals to the Earth. And, those on this picture.
But you also notice, though, and I'm sorry for interrupting, but you also notice that they are, if you go back just one, you can see it says field-aligned current, Birkeland current. I think the reason that I personally see right there, just, first link is Birkeland current. But one of the things for me, the reason I enjoy it, using Birkeland current, is because it immediately raises the question, who the hell is Birkeland? And the moment you do that, it is an eye-opening experience just asking that question because of what he stood for, and of course, his death, and of course, his debate with Sidney Chapman over the relationship of the magnetic fields, because that's a big conceptual thing to think of the
and the branch that formed.
Yes,
as well.
The branch that formed.
It causes the curiosity, right?
But I understand what you're saying, though, and I think that both of them are have valid points. So.
Well, I agree with you in this sense that it's a really well devised for propagandizing of EU ideas, that people would get involved by hearing this.
That sounds so evil. That sounds so evil.
Yeah. This is pretty much what I'm saying, is that it's kind of a dirty method of getting people involved.
Language is always always manipulative. Though.
Well, hold on.
It's a representation. Yeah. It's a representation of reality.
You're right. But hold on.
It gets into the pneuma and versus the sleeve.
For example, I'll just give you another example. The term Einstein-Rosen bridge. Okay, because of Thor Ragnarok and all those is why I'm using it, because it's something that anyone could recognize from those movies. But that term, the Einstein-Rosen bridge, is a real thing, just like the Higgs boson. And we give that as credence to the person who discovered it, because the essence is what Birkeland discovered was electric currents traveling from point A to point B through plasma, through intergalactic space, going into the pole of the Earth. That concept is different than the idea of the Earth as a magnet, if you know what I mean, like with a completed surrounding magnetic field. Even how they're drawn there, for example, the magnetic plasma shield of the Earth, for example, that's not how it really is. These are open magnetic field. Well, I wouldn't say open magnetic field lines, but they're much larger, and they go, reach towards the sun, if you know what I mean. And they have to deal with the magnetic fields in that plasma. Basically, the Earth's magnetic field does not exist as a separate entity. It is mingled and mangled within the solar and other planets' magnetic fields and plasma and so forth. I guess that's the big difference between the concepts. I'm thinking anyway.
But I can totally appreciate wanting to understand the history behind all of it, because I really am interested in that, obviously. But the point of the matter is that everything that you just described is a function, and if those things had been named per their function as opposed to someone else's name, then the people who read them would have a better idea of better idea and understanding of the thing that they were looking at. And then if their interest piqued them to the history of it, you know what I mean? We can go into that, but that's a problem that pervades science, is having these things named after people instead of named after their function. And in the same community that understands naming something at chemistry, if you put you put a tetra in front of something, it's 4. So then you add a bi in front of something, maybe it's 2. You know what I mean? Now we can start breaking things down. We can just look at that word and understand how that molecule is built. When you give something a name that gives it its function, you just can continue on with understanding its function, and then it makes it easier to understand. And that's what I'm saying, by calling them all Birkeland currents, it takes kind of that away, and it puts you in this other thing where now you're into you know what I mean?
I'm with you, but let me rebut, because I'm actually having fun with this, because this is actually very interesting. Because of its, and I would argue then, because of its unique qualities. Say, for example, the electric current aspect that I was referring to, with the traveling of ions into the magnetic polar regions of the Earth and so on, and creating the auroras, yada yada, all of that. Because of that comes with the concept of Birkeland, because Birkeland himself, he's synonymous with these concepts. But if we also go back a bit further, so let's go right back to Faraday. Now, you may or may not know that we measure capacitance in farads. Magnetic flux is measured in henries. Flux per square meter, I believe, is Tesla's. And then these concepts are, for how many ohms is something. Well, each of these things are called that, not just because of the discoverer, like ampere is how much current is going through something. Watt is how much power. But the reason that these are called what they are is because in some cases these concepts are something that you can't even put in a way into words. They have no analogy because they are things that you can't see. These are they're invisible.
Inductance and reactance have meanings. So.
That's true. But those are combinations in relationships. But anyway,
to give it the unit of memeasurement, the name. Okay, I can honor that. That makes sense. Right, because
just an idea. I'm just debating, by the way, not hardcore on this. I'm just having fun with it.
I know. I'm just
put your heels in.
Right. Yeah, a little bit.
I feel very strongly about this because words do free things. They're not boxes that things hide in. They free things. They allow them to be what they are. In the word freedom, right? You take the word freedom and you remove the concept of not being caged, and you take it as it doesn't have any cost to you. You take away the entire cost that freedom. Freedom costs a lot. Freedom costs a lot. If you say something is free, it means it has no cost to you.
Look at that DOM at the end. It's
yeah.
There's a song out there that says freedom costs $1.05.
Right.
Dollars to donuts.
I know.
I like this discussion as much as I dislike it, and for the same reason. Right.
It's good. It's great.
We can continue this argument forever because it's entirely philological,
And then we're using, to make insult to injury, we're using words to do it.
Yeah. So
it would ultimately lead to Buddhism, I'm sure, somewhere down the road.
It's kind of... It's basically a perfect topic for a talk show, where you can just shout it.
Can I add something here?
Well, of course.
We do.
And it is kind of funny. I have a heading on on one of my notebooks, and what I wrote down is, instead of Birkeland current, is dark mode, minimum energy configuration, field aligned Bessel Gaussian beam. And that doesn't exactly roll off the tongue,
but it's descriptive.
And what happens, the reason it's important, and there's so many mistakes that are made by thinking in terms of only one of those things. And I realized, like, Don Scott had the counter rotation right, but that only comes from the Bessel function part, right? That can be explained by the Bessel function part. But he tried to explain, and I did too, that Titius-Bode law from the Bessel function, and it doesn't work. That comes from the Gaussian part, and it comes straight out of that. So it's like, if you forget that it's all of these things, then you're going to miss part of it. Like the dark mode thing is what the mainstream sees as dark matter filaments, and they do the same thing that, dark matter's in the mainstream supposedly bends light. Well, a dark mode filament is something we won't see, but because a plasma bends light, it will do that. But you almost have to have all those words and descriptions, or you're going to try to place some of the behavior with the wrong term. Do you see what I'm saying?
I do. I think that,
but you lose a lot of the audience the second you add four or five words to describe one thing.
Right,
but some of these concepts are advanced, and you need to think about them in a certain way. And because as much as we would like to think about, I'm sorry, Jim, I'm going to be very brief. Much as you think of a straight, like just for example, just comparing electricity flow to water flow. Well, all of that sounds great on the surface until you recognize the right-hand rule is not something that's a property of water. It doesn't exist. You can mimic certain things with water.
Schauberger might disagree with you.
Okay, well, fair enough. But anyway, go ahead, Jim. I was just giving you that example.
Well, just because we did that, like, I was considering Bessel function, and then you immediately try to put properties, try to explain why a Bessel function should give you those behaviors, and it doesn't. And it doesn't have anything to do with that. So you need to include that it's a Gaussian, or so on. And it probably is still, we're probably still missing.
Right, but I mean, you can overcomplicate. I mean, the goal generally is Occam's razor, right? So how do you simplify it and capture all those things? That's kind of the challenge.
Well, the trouble is, it already has been actually, in a way, in a cosmological or grand scheme of things kind of way, much more, or almost solved anyway. In that sense, the Occam's razor is leaned so highly to the side of the EU. In my opinion, and probably, and I'm trying to be unbiased here when I say it, I mean, we can do plasma in a laboratory, we can watch what it does, we know these sparks occur, we understand why it's flowing. So at that point, it's just a matter of trying to understand that like in the novelty plasma ball, here comes the two twisted currents wrapped around the cells, reaching from the anode in the middle to the cathode on the side. Just like one of those novelty little thunderballs. Well, if that's the case, the theory that Jim is talking about is trying to describe the action of that line there, those two twisted currents. How do they work? What is the mathematics to describe something? Because we're basically trying to zoom right into that and trying to understand exactly, if I add up one particle, we know the particles move from point A to point B. We know that. How do they get there? What mechanism is making them move? Why? Like all of that. Like that is basically the mathematics of that. And we're beginning to realize how complex it is, but we can't deny its existence. So.
But then you could start, you could start looking at it.
Am I right, Jim?
By finding the simplicity, I mean, one of the things, like you say, a Gaussian on this, the type of thing, right? There's maybe not too much of a leap. Like instead of a Gaussian, you call a hyperbolic, and that's a much simpler calculation.
Yeah, and I also like. Am I not wrong? Is each one of those steps like 1 point, like the golden mean from each other ring? Don't they look like they're
not necessarily?
Not necessarily. Okay.
Yeah.
So, question.
There's definitely a certain danger, overcomplicating things. Like you can call water, this joke about dihydrogen monoxide.
Right. Well, actually, here's let's go into Chomskyan territory for a second. He pointed out specifically about the water issue. What is water is a concept that is different from H2O. You can think of something as H2O, and me and you and probably everybody here understands what H2O means, and especially Eugene. But the end result is we generally have a concept of what that means. Okay, so if that's the case, what is water? Because, well, it comes down to water is whatever comes out of the tap. It's amazing what we consider
the
water.
connotation of just the word chosen. Right?
Yeah. But anyway, I'm just giving you an example of how concept it can differ, even though a practical person would immediately say a factual person would go H2O and recognize it. But it's not necessarily the case of what we consider water, considering the contaminants that are in it and, other things like that. Anyway, just an interesting aside. Please go on.
So a Birkeland current needs a plasma, right?
Yes. That's pretty much a unit. And a metal in this case can be a plasma, by the way. Because the internals.
The next question.
I'm actually not sure that it needs a plasma.
Are you sure?
Are
you sure?
It depends on how you define it. Again, if you define it as just a current that is going along the magnetic field line, maybe you can construct this in some other types of environments, but I'm not sure.
Well, that's why I mentioned metals.
It would still need a carrier or a substance that provides
that can conduct
the means to create the Birkeland current structure.
Well, basically, you can take a coil, like a long coil, and that would generate a magnetic field in its center, and you can shoot electrons through this coil, and they would go along this magnetic field, and or you can maybe shoot a slightly charged liquid through it. That would not be a plasma in itself, but again, it would be kind of a Birkeland current, I guess.
I think that I use the term plasma very loosely compared to other people. Like I'm of the opinion things like lava is a plasma, even though it's very thick, and obviously metals in certain cases could be plasma. This almost becomes apparent when you put them in space cold welding. You can just touch two pieces of metal together in space and they are welded together. That's just an amazing property that seems to interplay something.
Excuse me, what are we seeing right now on the screen?
Oh, yeah, it's a plasma, by the way. Yeah, krypton. Yeah, I get the description. I thought it was pretty interesting, by the way.
It looks super weird.
Yeah, weird. Yeah.
Well, remember...
It's been told.
Remember, David?
We're dots. Here's an experiment we could do.
I'm reminded of David LaPointe's primer field video, and normally I try to distance myself from him because of certain conceptual errors, but I at least I think anyway. But I'm not going to dwell. What I think, though, that this kind of
whenever
thing,
there's experimental stuff like this, I'm really intrigued. But.
Well, he mentioned when he put them in the magnetic field made the balls have certain distance from each other when he dropped them into the center of his little experiment with the bowls. Well, in this case, I'm seeing a similar how they are self-organizing. This weird property of plasma is why I would think takes to understand this would be understand the basic premise of the universe in a way, because of this principle, the way that it can create as opposed to just destroy or entropy. And I find that to be fascinating. I mean, and look at it. It's just beautiful.
What's it doing? Yeah. So is this
picture of the Dendera tube, plasma tube, and compared to a plasma tube that we have nowadays, they have those little sparkles at the end of the glass ball.
Dendera?
Yeah.
So, the Dendera lights.
Yeah. They have those little sparkles at the end of the tube.
What is a plasma?
If I was the loosest, there's strict or loose interpretations. The strictest would be a material, a semi-gaseous material, perhaps dusty material that can conduct electricity.
Hey, Dave, let me just share for a second.
Wow,
I got
sure,
absolutely. Just for a second.
The very strictest would be something above a certain temperature so that it self-atomizes, but that's not obviously the case. Because clearly there can be dusty plasmas. You can see tornadoes and fire.
Okay, but let's go off that part. Let's stay to the fourth state of matter, if you will, right?
Well, clearly.
What I'm getting at is: are electrons actually separated from the atoms? Question mark.
Well, it doesn't.
Then you should define what means to be separated first.
Well, the standard expression, I believe, is that something to the effect like a plasma is a state whereby atoms are partially loosened, or electrons are taken loose from it, and because a plasma is a mixture of positive charged particles, usually protons, for example, and electrons. That's what they say it is. Right?
I would say it's a pretty close description to what it is. Yeah.
The only addition here is that, for example, any sort of a dust, we'll just go with dust or dry snow. Okay, at a certain point, it can become a certain charge separated from and of course ions electrons will build up between these, and you'll get that Gerald Pollack idea of the likes principle. And then they group together like he mentioned in clouds.
Isn't that Richard Feynman's idea?
I'm actually yes. Richard Feynman coined the phrase, but I meant Gerald Pollack. Dr. Gerald Pollack was doing. He used that term to describe how certain things will band together, and materials will have a fluffy density. I guess he was saying how they positives in clouds and so forth, and basically using his easy water theory.
Can you consider go ahead.
Ido, I guess you had some more general things to say.
Yes.
Well, what I'm struggling with is, are electrons actually really taken from the nucleus, or taken from the atom, if you will, meaning that the concept of a plasma exists of positive particles and electrons. Are they truly separated or not? I have a strong feeling that they are not. Because the electrons, why would they even stay there? They would, even out, leave the plasma, if you will.
But maybe on the contrary, maybe they would like to recombine to form atoms again, because they're attracted to protons, obviously.
Exactly. So are they really loosened completely or not? That's my question, actually.
I think they are. I mean, I don't actually have any problems with like conventional descriptions of plasmas, in the sense that, I mean, electrons would like to recombine with positives, but the question is, I mean, whether the plasma is stable in the first place. I mean, if you just heat the stuff up and leave it on its own, then definitely, due to its interaction with the environment, the heat would dissipate and electrons would again fall into these, potential wells of atoms and form stable atoms again. But if there's a constant heating up from outside, let's say, then you would have a more or less stable plasma where electrons would not fall into atoms again or something like that.
Would you consider fire plasma?
Yes.
Yeah, definitely, of course. Yeah.
Mm-hmm.
There's
so like that barrier between gas and plasma. Whereas, it's pretty easy to see, a solid liquid gas, but that gas to plasma what's that defining?
So why don't you get a shock from a fire?
Why don't you?
I did.
Well, if you put your hand in a campfire, I bet you would feel uncomfortable at least.
Okay, put your finger slowly. I'm sure you've done the trick. Wet your finger, put it slowly through the flame of a candle. You do not get zapped. Where are the electrons?
There should be a potential difference to get a zap, I guess. I mean, if you put a flame in between two electrodes, you would definitely see sparks. So that is one piece of evidence, at least.
There is a.
It conducts a charge, sure, yes. But I don't see any loose charge. That's my point.
Well, actually, you're not understanding. If I can, let me just answer you. Basically, when you have a chemical reaction, you know that there is movement of material from one point to another. This is going to create an area which you see on a match head, for example. You'll see an area where there's no flames right around the burning match head. You can see into that. Well, that's because basically what you're seeing is a chemical double layer. You're going to see that you're having a charge interacting down here. There's a space, and then you see they're trying to the oxygen is coming in, and of course the electrons are going out. And it's sort of in the same way that the sun works in that general principle. That's what I believe is I'm seeing here, which is why you're not going to have that's not an area. They're not interested in you because they're going in both directions at this point. If you know what I mean. You're having electrons rushing in, ions rushing out to try to fill this gap that it needs to try to get to basically do this conversion, this endothermic reaction.
Yes. So basically, when, for example, the fire conducts a current, I mean, in between two electrodes, let's say, it's exactly because the fire is more conductive.
They're making a plasma right there.
Than like a regular air. So this means that it has more free charge carriers, which means that probably a lot of atoms are ionized and there's a lot of free electrons. This is at least like the regular explanation. But I honestly don't see what's wrong with it.
Mm-hmm.
So this, again, this separation is fueled and it is like sustained by the influx of energy from the flame itself, from this endothermic reaction or exothermic, reaction. C turning to CO2 and so on.
Well, this is what it's all about, trying to understand. But to go even looser to the topic there, Edwin, you're going to see that you can see at certain points the same body of seawater, for example, could be a plasma and not a plasma, just as the same parts of the atmosphere could be a plasma and not a plasma. Because once you get anything like contaminated water can conduct, and if there is a reason for it to conduct, for example, underneath a water spout, it will. And so it will respond and begin to turn as if just like the air turns above it, except obviously it's a lot denser, so it will turn slower. But the concept is sound. There will be a reactance, and the inductive power of the magnetic fields dealing with the current going through the water would have an effect on the spinning of the speed of the turns and so on, and moving that water around would take energy, and there would be a resistance, physical resistance to that. So you can plot the actual VR curve, and you could actually plot the actual phase of the interaction of those two waves. So,
right, but what is rotating here? I don't see electrons rotating or anything like that, if you will.
Well, it would be charge, and yeah, technically, it's both. I mean, a certain amount of charge is ions, and a certain amount of charge would be electrons, and they are moving in opposite directions. That's basically
Neil, I actually have to correct you because even like pure water, not contaminated with anything, would also conduct, because water kind of dissolves itself in itself, if you know what I mean, because H2O molecules actually dissolve in other H2O molecules into H, which means protons, and OH minus, which means hydroxyl groups, right? So,
right,
even in like super pure water, there is a fraction of molecules which is dissolved. And the reason why we consider pH 7 neutral water, which means there is no extra acids, no extra, I'm sorry, I don't know the correct term in English, well, like, I don't know. Well, let's settle for acids at this point. So there's no like extra dissolved substances. So pH equals 7. It means that the concentration of
solution and soluble materials. I bet you what you're thinking of.
No, I mean there's acids and there's
bases.
This other thing.
Bases.
Yeah, exactly. Yeah. Thank you. Bases. Okay, so. pH equals 7 means there are no extra acids and no extra bases dissolved in this particular water, right? And what it means, pH equals 7, it means that there is a concentration of H, of protons essentially, dissolved in the water itself from the water itself. So, and it's equal to 10 to the minus 7, the concentration of these ions.
Oh,
because pH...
Edwin. Right there on the screen is smoke behaving as a plasma.
Yeah.
I would say it's like a remnant ionization from the fire.
Oh, clearly, yeah.
It's not that, the smoke itself is somehow conductive. It's just because there was fire before that.
Actually, I might disagree. Only because we've seen the fire tornadoes that came out of giant Burning Man and rolled across the desert as the dust continued to the current transfer, which was very interesting, and things like that.
Smoke is basically a plasma that's not ignited, a pre-state.
Yeah, it's
ready to burn.
It's just
that's the stuff that burns, actually.
Like
I would disagree with you.
Well, that's okay. That's okay. This is cool. But you're from Belarus, so it must get bloody well cold there. And where I'm from, it gets bloody well cold. So when it's really cold, the snow gets really, really dry. And when you're driving down the road at night, you can see these, well, we call them snow snakes. They go across the road, and they're tubes that are rolling in the wind, but they have a coherence that they'll stay together. That, to me, when I'm seeing that, I'm seeing a wind-induced magnetic field as these charged particles of snow are moving across and actually creating a Birkeland current. And just like this smoke is doing, or this fire is doing here. And they look like that when you're driving down the road. Do you not see those? Because to me, those are like, wow.
when there's like a forest fire.
I'm not exactly sure what you're talking about, but...
You don't get, I mean, it must get cold there. We just call them snow snakes because they look like snakes, but they're made of snow and they go across the road as you're, when it's generally windy and very cold. Because it's snow.
Snowflake.
Yeah, like dust rolling across. Now, I think in dust, it's a little bit more difficult to see it, but you must see similar patterns, Robert, in a spooky way where snakes of dust are rolling across the road. I'm sure at night, because I know where you live and it's dry,
Yeah, I've seen them out there. Yeah. They look like almost like horizontal dust devils, but they're just snaking across the ground.
Yeah, but they're coherent. They stay together. They're not made of just dust. We ignore them because we just don't think about them. But in all honesty, they are coherent. They stick together like a snake. That's why they look like one. They don't just... Sometimes they break apart and join back together again or whatever. And that's, but we never... I don't think much of it, but when I started getting into the EU, to me, that was yeah, I see this all the time. Every friggin' winter we see this. At least one day it's going to hit like -30. And when it does, I mean, there's going to be no moisture in anything, but there's going to be snow everywhere. And it just starts, you can even see it when it makes drifts. It starts, you can see little rips as it goes along across, and little lines, one on top of the other, like it's building, like it's carving, like one strip at a time. And it will make a little snow devil, like not more than maybe a few centimeters tall, or maybe a few inches, is just like that fire is there coming off, and the snow that loses cohesion after that. But it's just like these little things are ripping across the snow and carving the snow, little strip by strip by strip. And when I see stuff like that, I mean, I get an idea of what must have happened to the Earth at to like a canyon or something, or at a higher level of intensity. But I'm seeing the effect at a very low powered level, which I feel lucky that I can do that. But
we're going to need to see some evidence there, Neil, some pictures.
So basically, as I understand, you're basically talking about like something like dust devils, but with snow and not dust, right?
Right. Yeah.
Oh, okay. I definitely have seen some of those, like whirling bunches of snow, like up in the air or something like that. Yeah, but I don't see your point. What were you trying to illustrate with that?
Oh, I was just going that in the broad sense, you can be in a loose, dusty plasma can actually do some fair conducting. I think that we were all in agreement about the water. It was just a continuation of that kind of idea, that we're trying to see what plasmas are in deference to Edwin's original question. So,
okay, so I also want to add about this. A couple of years ago, I learned about this phenomenon of yukimarimo. I've spelled this word here. Yeah. It's peculiar balls of snow that people observe on the South Pole, and they are supposedly formed because of electrostatic attraction, I believe, and it's kind of a really interesting thing, and it also makes you think, about those concretions again that we observe around some mountains, for example.
See, I often thought, and thank you for bringing these to my attention, I have often thought that snow, people who live in very, very snowy, dry climates have the opportunity of watching, in some cases, electric phenomenon in a very low power setting, that it doesn't actually kill you. I can go out in this, and I've never seen, balls like that, but I mean, I can envision how they could be formed, how attraction could bring them together, much better than, conventional ideas. So,
but what's great in this case is that it's actually recognized that it's electromagnetism that make them happen.
Well, yeah, I don't think it probably formed exactly as a pinch, but I can see them collecting around a nucleus, just like snowflakes sticking together, so to speak.
So from what I've heard, a lot of these kinds of, concretions, I guess, are observed at the South Pole again, at the Antarctic stations, like Dome C and so on.
They look like cotton balls.
They're pretty small, yeah, but again, it makes you think, about those, for example, Martian blueberries and things like that. It's pretty interesting. Yeah, how even in super low temperature environments, I don't know, for whatever reason, those things appear. Maybe it's because of higher radiation in polar areas, because all of these currents actually land there. People working with space weather love working with Antarctica because it has very still air. Where these vertical atmospheric currents are super well, visible because there's no turbulence from, regular atmospheric phenomena there. So maybe this is the reason why these things appear there.
Well, you probably know this, but Antarctica is a desert. And it's It's a continent-wide desert, and there's very little precipitation, but except in certain areas, obviously, it's going to happen. But especially in the middle, there's a lot of, just barren land. But it's extremely cold and thus extremely dry. At a certain point, moisture falls out of the air. It just can no longer be there. It can't snow sometimes, if you know what I mean. And everything turns to very dry. Your nose will bleed, no problem. It's that cold. And that kind of thing is what I'm thinking would be the generator for things like this, because you're going to have high amounts of electrostatics, and that's what these drifts right here are carved like. They look like they were carved, just like it's not just wind, but you see how it has little layers. See those little layers,
looks like the wave.
And they're cut. They're cut. Yeah, exactly. And each one of those would just go zing, 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 zing right off of that, and you'd see these little tiny things go on by ripping them up.
So I guess,
Dave.
I guess what you're saying was that there's low humidity, and thus the existing charges have a hard time of recombinating or something, like discharging, like in a more ambient way, like they do in more temperate latitudes, right?
That would be my interpretation, yes. And I assume the same thing occurs in deserts for the same reason.
But at the same time, there's another factor that I mentioned, that there is a definitely higher level of ionization of the air itself in Antarctica than it is in equatorial regions, because of higher flux of, again, cosmic rays, solar particles, because they all tend to fall, into the polar regions.
You actually have a point, and I didn't mean to dismiss that. Because obviously, I think it would be a combination of the two, if not a perfect storm. Because I have experience with that here when it gets only on certain days, of course. It has to be really cold. It's not something that just pops up. But obviously, down there, it's practically always really cold. So, at a certain point, there's just no water there to facilitate any sort of, I'm not sure. I just know it's a feeling. I can't even describe it. At a certain point, you just know there's no more moisture in the air. Your lips will chap in seconds, that type
I know
of thing.
that.
Yeah, that's what I mean. You know what I'm talking about, but...
Yeah, but you mentioned my country. My country is completely different, actually. My country is very humid even when it's very cold. So at times it's almost like unbearable here.
Pittsburgh.
Like it's very humid in the summer, so it's unbearable because of the heat and moisture, and it's very humid in winter, so it's even more unbearable when it's cold. So.
It's bone chill, like Pittsburgh. Yeah, I get it. Yeah, the humidity does do its job on you there. Because Pittsburgh, you can have like 98% humidity in the summertime and like in the low 90s in the wintertime. So yeah,
wow.
It's your area, yeah.
No, the humidity where I'm from at certain times, and I'm sure it happens in other places, but it turns into, it's gone. There's no humidity whatsoever. At -40, your tears freeze right to your face, and your breath is, so. But that's rare, like I said. Electrostatic snowdrifts.
I was just trying.
Yeah, why not? But you see the original forms. Like if I can envision some of the situations that would occur in blizzards and sandstorms and so forth, or in blizzards and such with snow falling, look like land formations, but on a miniature scale. Stuff I would see in the American Southwest, if I was, being fair. And so I can envision certain things. It gives you an opportunity to see it in, like I said, in a just a non-devastating way. You don't. Oh, it's not incandescent fire welding to the ground. It's just snow.
Continuing this line of thought, I had a crazy idea just now that if dinosaurs could live on Earth sometime before, and if it was due to lower gravity, maybe these types of, smaller scale events that we observe today might have occurred on larger scale before, that kind of idea, due to, lower influence on the side of gravity.
Mm-hmm.
Because today they're kind of, damped because of this, disruption from the gravitation.
Well, or something caused the disruption to that and the gravitation. There could be a third factor or even more, but I'm with you. I see a relationship as well in that regard. I mean, we don't get these giant shelled animals. They just can't exist. Why? And that's not even getting into dinosaurs and the 9-ton thing. But I also, more and more, there's been more and more contestation of the, or contesting of the validity of because of geological aging being suspect, exactly how old. Like when we start finding DNA now inside dinosaur bones, whatever, and then you test it and you find that the age is somewhere in the 50,000 perhaps range. What does this really mean? Are we losing our collective minds, or because I'm not necessarily one for that line of thinking, but at the same time, I'm no longer certain of the age of any of this. The only age that seems to be remotely accurate would be stuff that seems to correlate. For example, that Mario Buildreps guy, because he was correlating with ice core data. Well, that gives us something, because apparently they can read that right. But now, I don't know if that's true, because I can only imagine what they're doing. I'm not a scientist who works on that field, so.
I think they're also measuring the concentration of different isotopes. So even those high score data, they're like, I don't know, I doubt them a lot.
Okay.
But, yeah. I mean, at least the scale. At least the scale. I mean, there are certainly some cycles present there, like, ice ages and stuff, but how long does it take? It's an entirely different question. How big is the scale of your, x-axis, so to speak, the time axis?
I gotcha. And that's my question too, because I can envision that because there seems to be certain patterns that we see in layers in the rock. That seems to be what we're seeing. Now, because of that, we watched that video on sedimentation not too long ago. I don't think Eugene was there, but it was a wonderful video discussing or showing how sedimentation occurs if it's water-based. But we're moving beyond that, of course, and thinking more of an electrical deposition kind of thing. But either way, the ages seem to be, correlate to, because we can see where things are connected, things that only exist in Australia and South America, for example, that indicate or Africa, and sort of have a connection, and we can start seeing that taxa connection and so forth. Does that really add to the depth of how far back that because we do see patterns, and it says that it's, this is 560 million years ago, but where, for example, the first flowering plants came before, where alligators came from or something, way back when, then there seems to be, till now, and there seems to be obviously changes along the way, mutations and so forth, that seem to come in regular devastating cycles. So they see these things, and we have to recognize that some of these things must be true, or at least, but now I'm questioning this whole aspect. It's like you have to go back and re-examine everything again with a fresh new set of eyes. And I just described what a paradigm is, so I should shut up and stop talking.
Kind of indicates the sequence. You can kind of bank on the sequence, I would say.
Speaking about the time scales, I remember a very interesting paper, from maybe 5 years ago, where people actually, what Moore's law is in transistors, like computer science, Moore's law. It basically states that the number of transistors doubles every 1.6 years or something like that.
That's right.
Okay. Yeah.
And so the people actually tried to find such a law in terms of length of the genetic code of living beings. So they basically mapped all the known species. I'll give you a link right here in the chat. So there it is. So basically, they've tried to map all the known organisms and derive this moral law for life, basically. So how long does it take for a genetic code to double in size, in terms of like evolution and whatnot? And they came to the figure of like the origin of life, which is like supposedly a couple of nucleotides, like the most simple, like, form of DNA, quote unquote, which is only like a couple of those nucleotides, which is twice as old as Earth, supposedly right now, like 4.5 billion years or something like that. So they came to this figure of 9 billion years. And it's just pretty funny. I mean, of course, one might think that this is an evidence for, this panspermia idea that life doesn't originate on Earth. But again, all those figures of the age of Earth and so on are so much in doubt, at least by me. I don't know about you guys.
Yeah. This thing.
But it's just pretty funny that it seems that they've seen the same kind of law there, same kind of logarithmic, increase in complexity, I guess, in genetic code that people observe, for example, in transistors in modern computer science. So maybe that would, I don't know, spark any ideas in somebody's mind. So I just had to.
There's there's interesting things that I've followed that, and it's always been like with it. We've reached the top, and it's we expect it to drop off, and it's like that's it's been doing that since the 80s. That.
Well, supposedly
but now it's because of parallelism. It opened up. The GPUs are doing 5 times Moore's law. Which is
at this point, there's also like this quantum limit right now when the transistors are becoming so small that supposedly again the wave properties of electrons should get in the way and kind of ruin the whole idea of transistor. Because electrons would kind of tunnel anyway to whatever the transistor you're constructing. So it's a kind of a long-standing, and by long I mean a couple of decades at least, problem in this.
Right. But now they're doing the parallelism is just like the GPU has 2,400 processors on it.
And it's also one of the reasons why people are obsessed with quantum computers, because they're saying, well, since we're already reaching this limit when, particles are waves and whatnot, and, well, you get the idea, probably. Yeah. So we should start using, quantum computers. It's a whole different topic, which is super complicated on its own, so I'm not sure we should consider
At some point, we could do that. If anyone's, and then there's silence. But that's been another big talk. It's just as far as how do you get logic, to show in there, and how stable is it? And I don't know. You're probably right. It's a pretty big rabbit hole to jump down.
Well, in terms of the main issue with quantum computing is, again, as you've stated, stability. So there's again this problem of decoherence. So maybe you remember our discussion a week ago when I talked about my PhD research, but where I utilized like the same formalism, but for quark physics, where we also use this concept of decoherence. So basically, the problem with quantum computers is that the quantum state of whatever you're using as quantum bits is too vulnerable for external influences.
Right.
So basically, your quantum state kind of degenerates, decoheres itself, or something like that, before you even achieve any kind of computation with it, you know.
Right,
so you should kind of construct it in such a way that those external influences wouldn't destroy it. And again, this is a problem of decoherence. How would you achieve such a state that wouldn't decohere at the times sufficient for your quantum computation to take place?
Right.
And it's a huge problem. It's like it's been there for decades, literally.
Right. Well, I mean, on the other side of it, the challenge is, you know, with these just massive planes of processors, the challenge is more like, what do you write? What kind of code do you write for them? Yeah, and that challenge is like climbing Mount Everest or beyond, obviously. You know. How do you take advantage of all that horsepower or like create something with it? And this is
now you've hit the nail on the head. And in a lot of ways, I think that this is a problem that has to do with this amount of power is allowing us to trick ourselves in a way where we think about like we've talked about this before, and I've watched this on certain television shows. For example, Stargate Atlantis talks about making replicators and that look like people, and he was just like, well, if it looks like and it sounds like, well, and you're like, but it's not.
It's really hard, yeah.
And that sort of thing, because we can imitate the complexities and make a wonderful game. And I trust me, I love my games, so it's no problem there. But it has to do with understanding what is really going on, as opposed to imitating.
The uncanny valley. You know that.
Yes, the concept.
Yeah. We do not even know the structure of the nucleus of the atom yet. So I don't think we're there yet, Niels. With the
well, this is one of the interesting things that's kind of coming up is one of the things that it enables us to do is look at super simplicity. This is kind of a theme that's been bubbling around a bit. It's like with all this power, it's like go way back to. I mean, you know, I've personally been dealing with tetrahedrons for a year now, and it's amazing. It's just amazing. This is like, who would think? Who would have thought that? Yeah. So, anyway,
what do you mean by super simplicity? Can you
like fundamental? Looking back at things from a more fundamental standpoint, using the tool for illustrating or exploring super fundamental things, like, you know, I mean, I know there's, you know, with the video games, you just build things out of all, you know, tons of triangles, but it's like, just look at the behavior of one triangle. And this is a fascinating pursuit, kind of crazy, perhaps like a Don Quixote tilting at windmills, but it's against your probably like it's anti-intuitive that you would do that, but it seems, at least from this standpoint, that it's producing some kind of very interesting insights into just fundamentals. You know.
Well, from my perspective, what is really anti-intuitive is that the deeper we're going into the matter, so to speak, like the more fundamental we're going, actually the more complex the matter becomes, you know, like the atoms behave much more complicated way than the regular bodies that we observe around us. And the nucleus of an atom is even more complicated. And again, if you go to the level of quarks and so on, it's just a completely different world that has no relatable laws in it. I mean, relatable to our everyday experience.
But obviously there has to be.
The nucleus is not that complicated, I would argue.
Yeah, I know.
But you are right that the properties of the elements are very diverse, and there are many things we can look at, from ionization degree to valence value to mass, short mass, and you know, gaseous state, whatever. There are so many attributes, and it's absolutely complex there. True, but still,
I just meant that, you know, again, what I said is counterintuitive, because what you would expect is that, you know, as you kind of dissolve matter into smaller and smaller parts, they would become simpler and simpler, and it's their like interaction which creates complexity. But what we really see is the contrary. It's actually the understanding of, individual particle, smaller and smaller, is even more complicated than understanding their, collective, so to speak. The understanding of individual quark or proton is more complicated than understanding the nucleus of an atom, or even the whole atom, or even the whole molecule. And it's kind of, I don't know. I believe it's a big, I don't know.
It gets philosophical from the perspective point.
That's the point, I guess.
Because you want to get something as precisely measured as possible and identify it, and you get the many all the time. It all just keeps on breaking up into more and more little particles.
There comes a point that our understanding is lacking because it's too fundamental. That's kind of what my conclusion was there.
But my conclusion kind of is that the very idea of atomism, that we can divide stuff into parts which are more simple than the whole, is false inherently, because we see practically, empirically, that the parts are more complicated than the whole. That's what I'm saying.
I would argue that is true in quantum mechanics.
Well, from my experience, this is true everywhere. And I would say that it stems from the fact that, again, this is my sort of epistemological position, that we are the farther we are going, the farther we are distancing from our everyday experience, the harder it gets for us to imagine things, to describe things. So the more fundamental, so to speak, we would go downwards again, so to speak, the harder it would be for us to even describe these processes, at least to the reality, And in this sense, I believe, again, that the atomistic ideas are flawed, because again,
the one that's very appealing to me is this continuum all the way down. Just continue. What's stopping us from modeling it? That it goes scalarly down 1 over infinity.
Well, I just said what's stopping, because it becomes more and more complicated.
Well, it's more and more complicated to measure, right?
Not only to measure, even to conceptualize, to give at least some picture. I mean, how can we imagine how these things work? That's what I'm saying.
This is the scalar.
It's hard enough with electricity.
Right. But the one thing that keeps coming up for me is this relation between scale and time. I mean, the durations of time. You look at it on a galactic scale. Obviously, you have these very, very large. The plasma, obviously, how it scales in time and volume. Right. This is a fundamental relationship that I find super intriguing.
My commentary here would be that I would love it all to be that simple, but from my experience, it's not that simple, unfortunately.
But isn't it a lot about measurement? It's measurement and having to put Aristotelian labels on everything.
Well, not so much measurement as, again, like conceptualizing, like the picturing what you measure, sort of,
Right. The model that works, unbroken, right?
Well, yeah, and it's like a whole different level. The model is already almost impossible achievement at this point, I believe.
Right.
Well, at least to have an idea what we're dealing with is already a start. But
although I think
we're not there yet.
I totally would go with Edwin, though, is when thinking about the electron, conceptually, it makes more sense, considering the weird properties of the electron, to be like a negative pressure, to be like the result of and the negative force generated across, like if everything had an equal plane, it would be like dents in that graph, in that plane, where there is a charge that's opposite to these nuclei charges, and so forth. And the reason I think that, is, for example, we know that you can just rub a balloon in your hair and stick it to a wall, but the amount of force that is used to stick that to the wall is way smaller than 1 electron volt, or 1 electron. Like the electron has just an amount of charge that, they've talked about it at EU things at length, where 1 electron can resist the force of 50,000 stacked 747s or something ludicrous like that. I'm not sure exactly what it was, but it was just a result. Yeah, well, it's because the electron has that much charge to resist that's why your knees don't smash together, your hip joints don't touch. Their cartilage is not incredibly smooth, not to the point where it's so perfectly smooth that it would not wear. But the only reason it doesn't wear is because it doesn't touch. Because there's electrons, there's a positive charge on each surface of your bones, and there is negative electrons built up between those two, and it stops you from touching. And that's why you can run without all your bones grinding together. It doesn't build up heat either because it doesn't touch. Those kind of weird things that they make me question so much about reality just there,
This is a great one. They put up, I think Robert might have mentioned it, but Fulgurites.
This is wonderful.
Peter,
Mungo, Jupp.
Yeah, it's really great. And one of the things that we've been exploring a bit, obviously, with is the Fulgurites and this transmutation piece. Speaking of things that I think are kind of like low hanging fruit for us to kind of chase after.
Well, it seems an almost impossible thing to ignore now. Especially that when we realize we can use incredible amounts of heat to create fossils, they're like, oh, because, it makes it much, to see this combination. I mean, we've also seen somewhat type of fossilizations in volcanic activity as well, where things were buried, Mount Pompeii, stuff like that. So.
Right. Have you seen these before? The emeralds, I guess. I was looking at this last night, but they're like biological emeralds.
What makes the determination that they're biological?
Because there's a shell.
Ah, well, that'll do it.
Yeah, like that. Right. Opalization.
Well, we've seen that happen to skulls as well, if I'm not mistaken.
Yeah, it's pretty fascinating. Right?
It's literally amazing. This is one of the things that makes me wonder about some of the things that Edwin was talking about. For example, Edwin, you mentioned that 2 oxygens combined together make a silicon or make a sulfur or something like that, and that parts of the human body would turn into, if they were combined, nuclei would turn into rocks, for example. And they're, when a la, instant fossilization. I was wondering, at some point, when we looked at, me and Robert were out there, and Robert's disappeared somewhere, but we were looking at Malachite Man, and it was the leg or femur of a bone, and it was made of malachite. So clearly, it doesn't necessarily combine the same elements both times, depending on the force that's being applied. You get different elements recombination if your fusion theory holds true. And therefore, some of these things can turn into opal or gemstones, which in itself is absolutely stunning.
Yeah, yeah. I mean, there's one where it's kind of like, and you see these things. They're talking about petrified wood, et cetera. That they happen because a power line falls down, and here he talks about it here, as I'm sure you've probably seen. But this seems to be like the one where you could pretty directly set up a lab experiment that you could prove, show this, and it's a type of transmutation.
Well, right? You don't actually need a lab. It's happened, as he was mentioning, and me and Peter got a chance to talk about and Edwin and I have talked about before, is literally the
this
power
is definitely a most fascinating topic there, Neil. Most fascinating. I don't have readily answers for anybody because we're trying to find this out together, right?
No, this is just a good question. We'd have to answer.
Right, and the body ratio. It struck me, if you look up the elements composition, the element composition of biology, the body, a tree, or whatever, then you find that, about 25% or so, 30% is carbon, and then you have like 2/3 of oxygen and a little bit of other stuff. And if you look at one carbon plus one oxygen becoming a silicon, you're left with some oxygen left. So that would basically imply silicon oxide, right? So yeah, it fits the bill. Is it true? I don't know. I haven't seen any evidence yet, right? It's a hypothesis.
Well, this is what I mean. We besides obviously the wonderful, almost gemstone-like petrified trees that we can see occasionally, and even petrified oil, which is a crazy idea. But we've seen that making some of the most beautiful gemstones now, amorite or something it's called. But and we talked about you guys talked about we talked about vugs, and we talked about kimberlite pipes and all those types of things. So
yeah, so to my mind, particularly the heavier elements are created on Earth in situ, through all kinds of processes and happenings that we hardly are aware of. That's my personal belief, if you will.
Right.
If you look at, if you do Google searches, etc., and you try to find, which is not easy, try to find what is known in the past 100 years about fusion processes, you will find, to your amazement, there have been a whole bunch of people doing all kinds of fusion processes and witnessing, for example, fusion between carbon and oxygen, for sure, in multiple experiments. And these are pretty solid experiments. We can say we don't understand it, we can say it shouldn't be possible, whatever, but it's happening. The transmutations are real. We can't control them. That's the big problem. But these transmutations are happening. I've seen many examples. My personal belief system of 20 years ago has been utterly shattered. I already live in a new world. Really.
I feel that as
there's no Big Bang. There's no star bomb going off, which is the sun. And heavier elements are created in situ. So, yeah.
Right. I think the game is really get something that we know we're solid on. And get it out into the mainstream. Yeah.
Well, the incident that occurred there with the, I believe it was a pile of clams on the side of a road, and a power line fell down. I think there was another instance which it hit a stump. But both of those instances resulted in those objects turning to stone, and piles of stone fused together. They look like a fulgurite in and of themselves. But obviously some of it had turned to different materials, from the biological, what it was, to stone-like materials. And I think he quoted it in here. But those type of events, which are unintentional, obviously, should be recognized as incidents which occurred. What does this mean? Can we exploit this? And I'm sure there must be people who are doing this. I mean, it would not be, considering what you can build today, compared to what you would need 100 years ago to do the same type of thing.
Yeah. But
that's difficult, actually.
Right.
No, but you want to do it in a smaller controlled location as opposed to what you would have to do in the past to make, do some of these things, is what I'm thinking.
It's more how you package it and getting it. I mean, that's to me. There's some kind of calling for that because I've certainly over the last 3 years as I dove in head first into this thing. It's like I'll talk to people who are unexposed to it and they'll be really compelled by it. So it's not one. I'm not saying it's suppressed. It's just there's no avenue to get it out more into the mainstream, and it is.
Oh, obviously not.
Certainly compelling. And important, I feel, just for just the everyone's perspective on things.
Well, this is what leads to this.
Can I tune in for a second?
Sure.
The old man here. I've been listening to this, and I called my son this morning, and I said, "I'll tell you what, we were at the 2017 seminar, and I just finally looked at this one here by Peter, and I was amazed by it." So I called him, and he said, "Yeah, I was just watching that this morning." But he was at the one in 2017, never told me about it. Now, 2 days ago, I was in Salt Lake City at a store that used to be a rock store that now has quit, and called the Vug, and they had a lot of different little samples in there. But in his glass cabinet there, and I wanted to take a picture of it, and I'm going to go back and do it, he had a natural-looking rock. It was sort of flat-surfaced and maybe cut out of a bigger piece, but the whole center part of it was sort of a rounded flat stone, and in it had about 7 or 8 craters that were maybe 6 craters that were maybe as big as a $50, like a thumbprint would be in a rock, pushed into it, and sitting in each one was a marble, a Moki marble. But it wasn't a foreign piece. It looked like it was exactly the same piece of this rock, which I had remembered that Jacob Gable the other day had one on there where he showed how you can form these Moki marbles that you were talking about just a minute ago in actual natural sand, which is exactly what this would look like, hardened sand with these things in it. And if it's natural that he didn't dish those out to put the balls in, it would be a really neat piece to look at as a specimen, because it would be and the other thing is, I live here in Duchesne, Utah, and was getting corn on the cob from this one farm that really got good stuff. But that's a nice design. She was telling me that when Bruce was here, Bruce Laybourne, we went up there and was with another friend of his as a geologist, and I took him there to say she has these petrified pieces of wood in her yard that are big. They're like 1.5 feet in diameter. So I was talking to her about it, and she said, yeah, she found them right out in the street, which was about, it's a dirt road off of where her farm is, but it was only about 150 feet away from where we stood, and it was the Morrison Formation, but it was a thin vein. And she said when they moved there about 45 years ago, these were almost sticking out of that vein. Now most of them are taken, but they're big pieces of petrified wood. And then I asked her about Moki marbles, because in Roosevelt, close to here, it was a Moki trading place. And I went in there and I asked the guy, do you have any Moki marbles? And he said, no, I haven't had any for years. He should have quit the name, I guess. But he was amazed that I had some. And I took them last year in 2017 and gave away about 40 or 50 of them on the table. So somebody got some of them. But she said right up over the hill was a place that has all these Moki marbles that you could go up, and they collected them their whole life and stuff. And so Bruce and I and this other fellow, he was having trouble come up from Mississippi and was really sick. He wasn't in a good feeling mood. But we couldn't find where she described. It was in an area where, unless you had a GPS, you might as well call for the Boy Scouts to come and find you. But we didn't find it. But she said her husband, for 30 years, was the school bus driver, and every spring. Pardon me?
I'm sorry. I didn't mean to interrupt. I was just comparing that rock that's in front of you to the moon Pan.
Oh, yeah, that's
Saturn's moon.
Okay, yeah.
Well,
it looks like
well, there's a moon that's shaped like that, believe it or not. Yeah.
But anyways, this bus driver every year would take the elementary school children in Duchesne up there to go hunting these Moki marbles. And she said that, so every person that went to school here in town has them somewhere in their bedroom. And so we couldn't find it. But that's how close we are to the geographic or the geology, not anomalies, but the evidences of electric discharges and electric universe. The one mine that's up here 6-8 miles from our house, I took Bruce to, is the yellow calcite, which is called honeycomb calcite. And they have about 8 million pounds of it on their property already cut into big blocks. They do some amazing work with it. It's translucent. It's beautiful. And it's the only place on the planet that they found this. But Mexico has what they call yellow onyx.
That's so damning.
And this, pardon me?
I'm sorry. It's just seeing the hollowness of it and the way that they're shaped and the way that they have a hard outer shell, but a different type of rock on the inside. And especially it looks like it has a high iron content. I'm drawn back to what Eugene has talked about earlier in the program with regards to the snowballs that were all like little balls in Antarctica. Imagine an alternately dry, high plasma environment making congealed balls of stone, and then, otherwise dropping them to Earth with a metallic coating. Because that's what you're going to get. I mean, that seems to be the way that things work. Like, for example, the Earth seems to be a metallic ball with a silicate coating, if you know what I mean. And that's probably how it originally started, and then things happen. Just noticing it. Please go on, Robert.
Well, I was just going to tell you that this location is pretty heavily involved. We're only about 8 miles from 9 Mile Canyon, which has all the petroglyphs all over the sides of the walls there, and which Peter also in his thing here we show a lot of the different symbols and signs. But it is the area that the electric universe, it is sort of the poster child for everything that we're looking at comparing on Mars. And an upheaval dome that I've dealt with for 20 years, that has put me through a course study where I probably know as much about upheaval dome as Gene Shoemaker and Bill Cassidy put together, because those two guys were arguing on my phone at $1 a minute when I was out here roaming about whether this rock had any silicate in it or none. And Gene Shoemaker said that it had absolutely no silicates in it, that it was totally calcite. And Bill Cassidy's arguing with him in Pittsburgh, saying that he and his associate had discovered there is silicate in there, but probably a small amount. And I'm standing there telling these two guys, I think you're both wrong. It's mostly all silicate and very little calcite, depending on what the calcite proportions were in the different layers of the sandstone in Moab.
From my understanding, this rock turned out to be something like a conglomeration of little spheres, if I'm not mistaken.
Well, it looks like just these pictures right here, but if they were minute size and you took millions of them and they stuck together, that's what I have. So the thing that messed the scientists up for 20 years, the second that I took it to first of all was Gene Shoemaker. And I got invited to see him on one of those peculiar things. It was almost like it was supposed to be. But I run into him, and he's at a lecture at Brigham Young University where he was invited to give the keynote address to his geology department. There were lots and lots of people. So he talked for 90 minutes about the iridium spikes that would appear whenever there's an impact or sharp quartz crystals, cone crystal, sharp quartz. And so I didn't really understand any of the 90 minutes of it. I didn't know what iridium was and why it would make a spike anyway. But at the end of this, I took the 6 rocks that I had up at the request of the head of the biology department or the geology department at Brigham Young University. He could not identify them. In fact, it was almost systematic. If you took it to a rock show or a rock person who loved rocks, they would say this rock was a lava bomb. And I didn't know what that was, so I asked, and they said, well, if a country rock falls into where the volcano is, it gets coated with lava, gets blown out, it kind of takes the shape of a bomb, and that's a lava bomb. And they'd say, well, then this can't be one, after they said it was, because it didn't have any kind of a country rock inside of it that the lava concreted to. So they would then go to it was just a concretion, but it didn't have any core to concrete around, and so they dumped that. And then they said that the fusion crust on the outside, which is very similar to Moki marbles, it's pitted, it looks like it's fused, whether it's the same material or looks more metallic, it has that same appearance, and inside it's usually like a white powder, like it's been all dried out, like the inside of a Reese's peanut butter cup that got exposed to the sun. Inside it's like chalk. And so that's what a Moki marble looks like. So when it went to Bill Cassidy, he took it to University of Pittsburgh lab, where he was the head of their whole English department of engineering. It was his engineering building. So he got upset because they could not tell what the elements were in it. The elements in sandstone in Moab were pretty obvious. And so he said, we don't have enough standards here at the University of Pittsburgh, which I didn't know what it was. And a standard, I guess, is a photograph of the real small elements, like quartz is an octagonal shaped piece, and they can look at that standard picture, and then they can say that's quartz, and the same with other minerals.
I got a question.
Go ahead.
Are we just going to gloss over the fact that you ate a Reese's peanut butter cup that was so bad that it was chalky on the inside?
No. I look at them at the date on the back, because I know Reese's peanut butter cups, and when they go bad, and I also know why they go bad. So thanks.
Actually, I have no idea why they go bad.
So on a more serious note, then.
Yes.
Okay. These Moki balls, these marbles in the desert, right? I have one over here as well. Picked it up myself during the geology tour, and we saw while somebody was scrolling, we saw a slice through where the outside is nice and dark with metallic, right? It's more iron content.
Well, I don't know that it's iron.
There it is.
Yeah. But that picture is what it would look like. But the inside is usually a lighter color, and it's powdery.
Yeah. Now,
like
so from the cold fusion field, it's interesting to note that calcium-14 plus oxygen is definitely a suspected reaction, if you will, at least through my eyes. And similar reactions are taking place, like carbon and oxygen do that twice. You have iron. So what I'm saying is, if you take electricity or some electric phenomena, whatever that exactly may be, into account, that created these spheres, then fusion with oxygen from the air, creating a higher iron content on the outside, is not strange suddenly. But the big elephant in the room is we must have meteorites explaining certain strange minerals, because that's exactly what you're tapping in on here. And obviously it's created through, if you look through the electric universe glasses, it's created through a big plasma electric event, which causes transmutations and resettling of all kinds of minerals, right? Different mineral structures. And of course they cannot make
apparently iridium
any logic of this because they totally ignore this concept. Absolutely, completely.
Absolutely.
Absolutely.
I heard something in the middle there.
Ido, I have a comment on iridium, which might interest you. I just had a super vague idea that maybe iridium is actually it's actually appearing during those events, during the discharge. Something transmutes into iridium or whatever else, but it just remains as iridium because it's stable, Because the mainstream explanation why iridium is so prominent in asteroids, like meteoroids and so on, is because iridium is stable. And since the asteroids are supposedly created from the same nebula as Earth was created from, it remains in asteroids in a super this remnant state. But on Earth, supposedly iridium, since it's very dense, it's one of the I believe alongside osmium, it's one of the two densest materials on Earth. It's supposedly migrated much lower to the core, like to the mantle and so on.
Right.
Well, I mean, the fact that there is such a thing as a KT boundary or something, there's something like a layer that has descended into the atmosphere from a big hit or something, that you can see this iridium layer, it means that it was pulverized right into fine dust and displayed.
No. What I'm saying is that maybe iridium is not a sign of the meteor impact itself, but rather a sign of a transmutation under the electric discharge event. That's what I'm saying. Which remained there as iridium because iridium is radioactively stable. So it remained, through these thousands of years.
Did that give away that this is correct? Did that give away that this is correct? Is a phenomena called, what's it again, those radial spheres in diamonds and in silicon oxide, in granite, etc. Radio halos.
Polonium halos, actually.
The polonium radio halos. Yeah. It's a huge controversy. Now, mind you,
don't go off the screen, Dave.
If you Google it,
I want to see something down there.
Explanation for the creationist.
Right there. Okay.
And you will find an explanation for millions of years. But the whole point here is those polonium radio halos could not have been logically. The polonium exists for minutes or something to that effect.
Correct.
In half-life. Meaning you have to find a way to get all that very radioactive polonium together, grouped, a whole bunch together in the rock material, spread out fluid rock, all kinds of little nucleuses there of these groupings, and then I mean that's totally impossible. So that is a very, very big piece of evidence in my mind for in situ creation. And as you pointed out, Eugene, that iridium is much more stable, so that will stay there. And yeah, it depends, of course, on your circumstances, what kind of elements you have there, how long the duration of the event is, exactly what's going on, what element you get. But yeah, this is true.
What you just said, Eugene,
I just wanted to add that I don't endorse this point of view. I just had an idea that it might be the case.
No. Your point is valid. For example, can you just go up slightly, Dave, because this is related directly. If you see the mysterious Milky marbles in Zion, okay, right there, that picture.
Here.
No, that one. Yeah. Yeah, that's the one. And you see how they're embedded in this rock. Now, they're not embedded because something jammed them into this rock. They're probably all through this rock. And they are part of an event that some of it was completely fine dust, building up like snow or whatever, and these things fell and landed in it. And now they are there, basically. And as it goes up, just like the polonium halos you were discussing, which have the exact same situation. Basically, you have a polonium halo, and you know it's a halo because this little piece of radioactive material landed on this growing thing, was encapsulated, and more or less created a sphere around it, which means that this rock must have formed within that length of time. So we know a time frame. Basically, it was probably, minutes or seconds at least, something in that range, to fill that halo, which the halo is not that thick, but it still gives you an idea on how much it would. 1 centimeter in just a few minutes or a few seconds. That's a buildup, really quick buildup. So this is what I'm seeing.
But how can you be sure that those layers couldn't have been created like a few centuries? Let's say if there was like a constant stream of plasma or whatever.
Because if it's a polonium halo, if a polonium atom had fell onto a surface and it was building up over centuries, you would only see a half circle. You would only see
You would need a constant polonium source still, and since polonium decays in minutes,
and it forms a sphere.
What's the source? You need that means already still in situ creation somewhere. Now, unless you can find a process that comes from a dying supernova, screaming and all, with a constant feed of polonium to the Earth, it doesn't make sense.
Actually, it doesn't make sense that way either. But
no,
wait a minute. Wait a minute. I just want to ask a question to clarify. Do we see the same concentrations of polonium in all of these spheres on this picture?
Oh, no. I'm comparing
the
what you're
polonium
seeing
are
here.
not in these spheres.
Yeah.
They are microscopic. You need a loop to see them.
Yeah, but it seems to be proving the same point. Basically, since all of these we would argue that all of these balls are made in the same event. Well, if all of these balls are made in the same event, electrically speaking, then it looks like millions of years had gone by while they were falling from the sky, and building up. That doesn't that seems illogical.
But that's what I'm asking. How do you know whether they were created in the same event? Maybe that
they're
was
clustered
a
together.
constant process. Huh?
I just mean they're clustered together. It looks like what would be the chances that they weren't? That's all I mean.
That's the problem. Radiometric data goes out the window.
But when you look at yeah, exactly. If you have this incident,
do they have the similar content in terms of elements, or what do you think they're from the same event?
They look to me that they are electrically induced pinches or static. And for a new idea that you had brought up, this statically induced globs of sand that would be like globs of snow, those snowballs that we saw in Antarctica, very similar to those. But they are getting cooked in this field and collecting, because of their differing charge, are collecting perhaps maybe an iron-rich version of themselves, depleted, that are sticking to the outside of these things, and they are falling to Earth through an atmosphere or something, or rolling around. But considering they have a certain shape, a radius, around themselves, and a polar sort of configuration, then obviously they must be they are probably electromagnetic, so they're probably from a pinch, just like and they have a magnetic field, at least for a time. That's what it seems to be, anyway. But this is something that we know is an effect. I mean, we know that if you charge a bicycle, you can spray paint both sides at the same time, with a 12-volt battery, because the paint will go around and stick to the bike on the far side. It's a very interesting effect that if you were my generation, you did that occasionally. But the polonium halos adds the other aspect to it, because we do know the polonium has a very short half-life. And if that's the case, then this atom would hit the material, land there, from wherever it came from, land on the surface of the Earth in that formation, and it would leave a half circle, basically, because it would only affect the ground underneath of it at the time in the 7 minutes it was there. But what we see is a polonium has a complete halo. It's completely wrapped around in a full 360 in all directions. It's a full volumetric sphere. If that's the case, then that means that it was encapsulated inside of dirt. It hit the ground and encapsulated inside dirt, and on all sides, the radiation decayed relatively evenly. That means that it must have happened in the buildup was so fast compared to the 7-minute half-life that it was negligible to the effect of the sphere, because as you can see, the spheres are pretty much 360. So, in fact, I don't know any of them that aren't perfect. So, it's just an interesting, damning thing with regards to materials, because they decay so quickly. There's no way this could be. They had to form relatively instantly, basically.
That's a great point. Yeah, I love that. Just because it kicks ass,
Well, but I don't like to think that way necessarily. I mean, but it brings the point to how violent and how quick were these buildups. I mean, you can imagine then that you have rock building up, literally just sticking there like it was falling faster than snow falling in a blizzard. In basically going at least inches per second, or maybe slightly slower or slightly faster. I don't know, but that's a quick buildup, a very violent event. There'd be no moisture in the atmosphere, a total plasma. The dust balls would be suddenly congealing to themselves, thrown up into the air, pinched, and then you'd have a shell would be attracted to them. This whole thing would be falling, and it would be just gluing itself to the Earth as welding tuft, basically. And it would sort of sort itself in the air, as we know that plasmas do, just like we see on the sun, how it comes up it's drawn out, material is drawn out of the sun, and sometimes it falls back, but obviously it's not falling back in the exact same position. So if we can think about it in those terms, the same thing probably happens on the Earth, where that's why we walk through a canyon and we can see looks like a blob of rock over there and a blob of sandstone over there, and you're like, what caused this? So that's what I'm, I mean, obviously Andy had the similar thing when he's talking about the violence of the shock waves. They must have been intense as well. So, it was...
And it kind of explains why, 98% of all the species that ever existed on Earth are extinct right now. Yeah?
Yes, and it seems that, and of course, if you look at like some of the time frames, like Saturnian Cosmology with Joan Cook, his ideas, he was trying to reconcile the fact that there is a time when flowering plants seem to come around, and there is a time when, there's been successive extinction and then speciation just afterwards. And this happens over and over again, every apparently 26 million years. This is why he then related this idea of Saturn coming and going and coming and going, and we were dropped off here or something like that, and then we eventually got caught up in this whole thing again, which was the last, ideas of catastrophism, which enters into the Velikovsky Talbot area of the ideas. But I'm not dwelling on that. I'm going with the fact that there does seem to be these events that seem to be recurring. We shouldn't ignore that. I'm not sure exactly now. I want to look to figure out how it was gauged. How did you determine it? And I'd like to see it with new eyes. But it doesn't necessarily mean it was that long, because now we don't understand dating. It could be variable decay rates. If, electrically speaking, the charge is different, that could be affecting that. If that's the case, and there seems to be evidence that it does, then we don't know the actual ages. So they might stick together. There might still be like a compression of time, like instead of 56 million years, it's 56,000 years or something along those lines, or we just don't know, at least not yet.
Well, my personal view is that the most recent catastrophe has happened much closer to us than we think. I think I'm more or less subscribed to this Gunnar Heinzon idea, that like the year 230 is equal to the year 930.
The 700
right.
700 year difference of the Dark Ages. Flamenco, I think.
What moved you into that position?
Well, I've watched his presentation from, there was this conference in Toronto organized by Julian West and some other people in 2016, I believe. And me and Neil, we've met Julian on this geology tour at the EU 2016. And I remember we were, present in this hotel room where he gave his presentation on Jupiter after the geology tour. But anyway, so... I
feel so bad for falling asleep to that. But I was exhausted when I got done.
Well, yeah, it was really late. Yeah, we had.
I tried. Yes.
but anyway, so it was a great tour. Yeah. And actually, those pictures of these concretions, they were from Zion Canyon, right?
I noticed that. That's what I was going to say. I didn't bring it up, but yeah, we saw them there too.
We were there, right?
Yes, we did. And we also saw some in Zion Canyon. In addition to that, we also saw one of those wonderful blasts. The sort of dent that you see in the rock from a shockwave impact, where a front hits it. It's like a hole, almost like a hole in the rock, like it hits it like a bullet. It's just interesting that we saw it there, and the canyons were incredibly steep. There's Bryce right there. That's beautiful.
Yeah. Well, my biggest highlight from EU 2016 geology tour was Cedar Breaks, if you remember that. It was just such an amazing place. It was like on top of the super huge plateau overlooking like I don't know, a valley, I guess. And it's in Utah also.
Yep.
It was just great because it was summer, but on top of it, those cedar breaks, we saw snow and there are some, like, you know, familiar vegetation there.
Well,
like
I had
trees
to.
and stuff. Yeah.
I mean, come on. You put me on a place
Yeah,
and someone goes,
I
there's snow
remember.
over there. I went like,
snow, yeah.
I did.
Listen.
I basically took a knife. That's what I took a knife and cut the layer that had all this, you know, the forest goop, we'll call it. And then I got to the fresh snow underneath because I didn't want to throw a snowball that was dirty. It would be un-Canadian of me. But yeah, I definitely had to throw this snowball at somebody. I mean, it's the middle of the summertime. I'm here on top of a mountain, and now I found snow. Someone's getting hit with a snowball. I'm just saying.
Can I say something here real quick?
Of course.
Well, I don't know how to butt in, but I try to. This is also y'all of Utah. And just as I was going to get done at the end of that last thing I had to say was, for the next convention, which will be in Denver, depending on time, it's somewhere between May, I guess, and August somewhere. Bruce Laybourne and I, and I guess some other people he's already talked to, have planned a geology tour for 2018 that will begin in western Colorado, around the dinosaur lands there, and then come through Vernal, Utah, which is the dinosaur capital of the world. And it looks like it might break down into, at this point, 3 segments. There'll be a daily tour for a week where people can sign up to go on day tours after the convention. And he's planning to have a 1-week outing. And for those who have the stamina, a 2-week outing, which would go to places like Skull Valley and the Slot Canyons. And when Andy Hall was up here, he found the Slot Canyons that had the flat bottoms and the perpendicular walls, which would not be eroded. And outside of those was the fossil things that they found. So there's a lot of that in the works. And if you're interested in looking into that, kind of keep pestering the people to get it arranged.